Okay, in this video, we will first recall some basic facts about topological groups. So let G be a topological group. And recall that this means that G is a group and it's also topological space such that the group operations are continuous. And as a consequence, we can consider the following map on the Cartesian product with the product topology. So this is a map delta. You might think of this as a difference map, and what it does, it sends a pair to the product of G of the first component with the second component inverted. So this is a continuous map. All right, so we will in this video use this map delta as an auxiliary map to prove some statements. But before we go to the statement we actually want, I want to remind you, so if you have any subset of G and O an open subset of G, then we have the two sets O times S. So we're using here the set notation. This basically means that those are all the products where O is in O and S is in S. And we can also take the product the other way around, where we have the same setup, but now the order of the products is always the other way around. And since left and right translation with fixed elements are continuous, it's easy to see that these sets are open. So since O is an open subset, these product sets are, again, open in the topological group. All right, so we need these two preparations. We need the delta map and we need this insight that these product sets are stay open if one of them was open. I mean, they were one of the sets we multiplied. And what we want to do, we want to prove the following lemma. So if you have a Hausdorff topological group and an element in this group, we call it G, and another closed subset C, which does not contain the element G, then there are open neighborhoods both of G and of the closed subset C, such that those two neighborhoods do not intersect each other. Okay, so how does the proof work? So we will need this auxiliary result later. So since C is closed, its complement in G is open. And let's call this complement here O. So we take G without C. This is open. Great. As the element G is now in this open subset, since it's not contained in C, we see that as well, if I take delta of G and then the unit, this is G times the unit inverse, but the unit inverse is the unit, so this is G. So we have that G times the unit element, so this pair is contained in the pre-image of O, and since the pre-image of an open set under a continuous map is open, so this is an open subset of the Cartesian product. And now we use the properties of the product topology to find open sets. So G is contained in U. This is an open subset of G. And the unit element is contained in a set we call W, and this is also contained in G, and both of them should be open. So we can find these two open sets such that the Cartesian product of U with W is contained in the open set, which is the pre-image of O under delta. Okay, let us consider now an element Y which lies in the intersection of U and with C times W. So we can write Y as C times W, where C is in C and W is in W. And so So let us, so since the W is in W, we have basically this nice pair YW. This is in U times W, and this is contained in the preimage of O. Okay, so let's see what this brings to the table. So if I compute just YW, this is of course by definition Y times W inverse, and so we know that this guy needs to be in O now. But since Y is C times W, we have C times W inverse. So this is equal to C. And this is also inside of C. But now we have a problem because by definition, the O was the complement of C. So such a Y cannot exist. So we have that actually the intersection of U with CW needs to be the empty set. Okay, recall now. So first of all, by construction, G is in U, and C times W is so U is an open set which contains the set C. This is of course due to the fact that W contains the identity element. So C is inside of C times W. So we have found two open sets. U was open, it contains G, and CW, which is an open set which contains C, but they don't intersect each other, and this proves the lemma. So we are done here with this proof.